Today we're going to talk about continuity and limits, and we're going to touch on the intermediate value theorem again. I say again because we've talked about it at least once, I think twice this year, and it will come up again. But the big thing is to understand continuity and the various types of discontinuity. I do want to warn you, so just like with a lot of things we've seen in this unit, as well as a lot of things we'll see this entire semester, a lot of this is going to look very formal, and that's because in order to have the math be very robust, I guess someone might say, it needs to be very formal. It needs to have these definitions. So this is stuff that back in the day people had to come up with so that others couldn't argue with them about the math that they were creating. So that's what we're doing here. So there are three conditions that exist for which a graph of f is not continuous at some value c, where c is just an x value, okay? So here I have an open interval from a to b, and f of c is not defined. So there's just a hole there. That's one way in which a function would not be continuous at c. Here, the limit as x goes to c of f of x does not exist. So if the limit doesn't exist, the function can't be continuous. And then the third scenario is the limit exists, but it's not the same as the function value at c. So that's the third scenario. So what does this mean? So this is our definition for continuity. At a point, a function f is continuous at c if the following three conditions are met. First, the function is defined at c. Second, the limit as x goes to c of f of x exists. And third, the limit as x goes to c of f of x equals the function value at that point. Again, as I said, this should make sense. It's kind of common sense in a way that in order for something to be continuous, it has to exist. The limit has to exist, which that's just telling us then from both sides it's approaching the same value, and the limit and the function have to have the same value. That should make sense. So continuity on an open interval, a function is continuous on an open interval AB if it is continuous at every point in the interval. A function that is continuous on the entire real line, negative infinity to infinity, is what we call everywhere continuous. Okay, so real quick, let's make sure we really understand what it means to be an open interval versus a closed interval, because these are words that come up a lot in these definitions. And again, they sound really fancy, but they're not. So open interval is when we have our parentheses. Remember, that just doesn't, that means we don't include the endpoints. So there are no defined endpoints. An open interval, something like this. So where this is our A and this is our B. So that would be an example of an open interval. Now I do want to point out, an open interval could also be all real numbers. So negative infinity to infinity is an open interval because remember, negative infinity and infinity are not actual values that we can get to. So then a closed interval, well, that's when we have the brackets. So we're including the endpoints. So let's draw a picture. That's my A now, and that's my B. That's a closed interval. So that's what we're talking about when we say open interval versus closed interval. Open interval, no defined endpoints. It doesn't mean that it's negative infinity to infinity. It could just be some segment, but we're just not including the endpoints. Or it could be negative infinity to infinity. But closed interval, we have defined endpoints. All right, so the previous definition was continuity on an open interval. So definition of continuity on a closed interval is a function f, a function f is continuous on a closed interval AB if it is continuous on the open interval AB. Okay, so it has to meet that definition. And the limit as x goes to a from the right of the function is the function value at a, and the limit as x goes to b from the left of the function is the value of the function at b. So the function f is continuous from the right at a and continuous from the left at b. That's our definition of continuity on a closed interval. So discontinuity. Consider an open interval I that contains a real number c if a function f is defined on I except possibly at C, and f is not continuous at C, then f is said to have a discontinuity at C. So if it's not continuous, then it has a discontinuity. Removable discontinuity is a discontinuity at C is called removable if f can be made continuous by appropriately defining or redefining f of C. So, like I said before, think about a hole. Non-removable discontinuity is a discontinuity where f cannot be made continuous. So think about an asymptote or a jump. So properties of continuity: if k is a real number and f and g are continuous at x equals c, then f plus g, f minus g, f times g, k times f, and f over g, assuming that g of c is not 0, are also continuous. So that's just saying that if we add, subtract, multiply, divide, multiply by a scalar, any two continuous functions at some value, then that result will also be continuous. The following types of functions are continuous at every point within their domain. We've actually talked about this earlier in first semester when we talked about polynomials, rational functions, and radical functions. So these functions are continuous everywhere within their domain. It's very important that we understand that this is within their domain, because rational functions and radical functions do not have a domain of all real numbers necessarily. They can, but they don't have to. But they are still continuous everywhere within their domain. Polynomial functions, they have a domain of all real numbers. Okay, so let's try some examples. So for the function at the right, I want you to find the limit as x goes to c from the right, the limit as x goes to c from the left, and the limit as x goes to c. Then determine if the function is continuous at c, state why or why not, and if not, is it a removable discontinuity. Pause the video, do that, unpause when you're ready to check. Alright, so hopefully you figured out that the limit as x goes to c from the right is -2. The limit as x goes to c from the left is also -2. Therefore, the limit as x goes to c from the left and the right is -2. So the function is continuous at x equals c. And our reason is because it meets our three qualifications. F of -2 is defined, the limit as x goes to -2 exists, and the limit as x goes to -2 of f of x equals f of -2. So we don't have to worry about e because it's not applicable here. Alright, I want you to try this one. Same idea. Pause the video. Unpause when you're ready to check. Alright, so again, the limit as x goes to c from the right, or as x goes to -2 from the right, is 2 in this case. The limit as x goes to -2 from the left is also 2. Therefore, the limit as x goes to -2 from the left and the right is 2. Is the function continuous, though? No, it is not. Again, this should be obvious. Like, I see that. But why is it not? Well, it fails the third requirement. So it did meet the first and second requirement, where f of -2 was defined, the limit does exist, but the limit as x goes to -2 of f of x does not equal f of -2. Is it a removable discontinuity? Yes, it is, because this is a hole. We could come up with a different function that is exactly the same everywhere except for at the discontinuity, and then would therefore be continuous. Next one, same thing. Pause the video. Unpause when you're ready to check. Okay, so here the limit as x goes to -1 from the right is 0. The limit as x goes to -1 from the left is 2. Therefore, the limit as x goes to -1 does not exist from the left and the right. So the function is not continuous because the limit does not exist, and it is not a removable discontinuity. Alright, so I want you to prove that f of x equals absolute value of x is continuous at x equals 0. By prove, I really mean just show. It's not really a proof. Pause the video, unpause when you're ready, show. Alright, so for a question like this, really all you're doing is you're just showing that all of our three requirements are met. So the function exists, the limit exists, and the limit equals the function value at that x value of 0 in this case. Alright, I want you to try this one now. Find what value of a will make this function continuous. So pause the video, do that, unpause when you're ready to check, and think about the requirements. Alright, so the first thing I notice is that each piece of this piecewise function is a polynomial, and therefore remember that a polynomial is continuous everywhere. So the only possible point of discontinuity of the piecewise function is where I jump from one piece to the other, which happens at -1. And so all I need to do is I need to figure out, okay, what is the current y value when x is -1? So I plug in -1 to the piece that includes -1, which gives me -1. And then I need to make this other piece have that same value. So if that happens, then the limit will exist, the limit will equal the value, so I'll meet my requirements. So I do a times -1 squared plus 2 equals -1. And again, this -1 here is because that's what the function equaled. This -1 is because that's what I'm plugging in. So when I solve that, I get a equals -3. So if a is -3, this piecewise function will be continuous. Alright, so now let's look at the continuity of a composite function. So if g is continuous at c, and f is continuous at g of c, then the composite function given by f of g of x is continuous at c. Okay, so now we want to think about the continuity of the following two functions, or the following functions. So if f of x is the square root of x and g of x is x squared. And then we also want to think about what if f of x is 1 over x and g of x is 1 over the square root of x. I'm sorry, f of x is 1 over x and g of x is 1 over x minus 1. I apologize. So I want you to pause the video and think about what the resulting continuities are going to be for these, for the compositions for h of x. So that's what you're trying to figure out. What is the continuity of h of x? Pause the video, unpause when you're ready to discuss, because that's what we're doing, is discussing. Okay, so the first one, h of x equals the square root of x squared, which, remember, that simplifies actually by definition to the absolute value of x, which is something that is continuous everywhere. So h of x is continuous for all real numbers. Now, if I look at this definition up here, I know that g of x is a polynomial, which is continuous everywhere, so g of x is continuous at x equals c, and f then is continuous at g of c. So this meets my definition, it's continuous for all real numbers. Down here, it's a little trickier, and this, remember, really what we're talking about, so we're defining continuity really formally. Really, it's just talking about the domain of a function in some ways. I mean, there's not exactly, but there's a lot to do with domain. So if I compose f of g of x, which is h of x, I do 1 over x minus 1. I don't like the division of fractions, so I multiply the numerator and denominator by the reciprocal of the numerator, which is just x minus 1, and I end up with h of x is just the function x minus 1. But remember when we did composition of functions back in first semester, and we talked about how does the domain work? Well, the domain is restricted by the function that we plug in. So the restriction on the function of g of x is that x cannot equal 1. So therefore, although h of x simplified to a polynomial, it still can't equal 1. So this is continuous for all real numbers except for at x equals 1. And I also know this is a removable discontinuity because of the fact that this is a polynomial. So I know I can write this polynomial where it does exist at x equals 1. So that's what makes it removable. Alright, the last thing we're going to talk about today is the intermediate value theorem. We have talked about this before. All it says is that if f is continuous, so now we're bringing it back up because it has to do with continuity, on a closed interval a to b, and k is any number between f of a and f of b, then there is at least one number c in a to b such that f of c is k. We've done this before. We've used it for approximating zeros. You can use it to approximate any number, but really the usefulness that we've seen before is for zeros. And again, it's really a common sense theorem. It's an incredibly important theorem. It leads to other such theorems as the pancake theorem and the ham sandwich theorem and cake cutting, but it's very important. It's kind of common sense. It's just saying if I've got some point here, and I don't know what this looks like, but I know it's continuous, therefore I have to hit every y value between these two y values. So if I know this was a negative y value, this was a positive y value, I know that a 0 had to be between. That's one example. Conclusion, function is continuous at a value if it is defined at the value, the limit exists at the value, and the limit at the value is the same as the function at the value. understand open intervals and closed intervals because they come up a lot in the definitions.